In the last two lessons, we went forward from f of t to f of s. Now we go back. Inverse Laplace usually looks scary because the definition is a counter integral, but in circuit analysis, we almost never start there. We do something much more practical. Rewrite f of s into simple pieces, then match each piece to a table entry. So the skill is not memorizing a new integral. The skill is algebraic cleanup plus pattern recognition. Start with the core idea. If 1 over s plus a transforms back to e to the minus at, then 3 over s plus a transforms back to 3e to the minus at. Linearity lets us invert term by term, so if f of s is a sum of simple fractions, inverse Laplace is easy. Each denominator gives a time mode, and each numerator gives that mode's weight. The whole game is making the expression look like a sum of recognizable table pieces. Here is the partial fraction workflow. First, make sure the rational function is proper. The degree of the numerator must be below the degree of the denominator. If it is not, divide first. Second, factor the denominator. Third, write one unknown coefficient for each simple piece. Fourth, solve those coefficients. Finally, invert every term using the Laplace table. This is the bridge between circuit algebra in S and actual time domain waveforms. Keep 4 inverse pairs in front of you. 1 over s plus a gives e to the minus at. 1 over s plus a squared gives t e to the minus at. Omega over s squared plus omega squared gives sine omega t. And s over s squared plus omega squared gives cosine omega t. Most transient circuit answers are combinations of exactly these shapes: decays, multiplied decays, sines, and cosines. Example 1. Different real poles. Let f of s equal 2s plus 5 over s plus 1 times s plus 3. We split it as a over s plus 1 plus b over s plus 3. Multiply both sides by the common denominator. Now 2s plus 5 equals a times s plus 3 plus b times s plus 1. To find a, set s equal to minus 1. The b term vanishes and we get 3 equals 2a, so a equals 3 over 2. To find b, set s equal to minus 3. The a term vanishes and we get minus 1 equals minus 2b, so b equals 1 over 2. Therefore, f of s is 3 over 2 over s plus 1 plus 1 over 2 over s plus 3. Inverting term by term gives f of t equals 3 over 2 e to the minus t plus 1 over 2 e to the minus 3t. Read the answer like an engineer. The pole at minus 1 creates the slow mode e to the minus t with weight 3 over 2. The pole at minus 3 creates the faster mode e to the minus 3t with weight 1 over 2. The farther left the pole is, the faster the decay. Partial fractions are not just algebra, they tell you which natural modes are present and how strongly each one appears. Example 2. A repeated pole. Let f of s equal s plus 4 over s plus 2 squared. A repeated factor needs a full ladder, a over s plus 2 plus b over s plus 2 squared. Multiply through by s plus 2 squared. We get s plus 4 equals a times s plus 2 plus b. Compare coefficients. The coefficient of s gives a equals 1. The constant term gives 4 equals 2a plus b. Since a is 1, b equals 2. So f of s equals 1 over s plus 2 over s plus 2 squared. The first term gives e to the minus 2t. The second term gives 2t e to the minus 2t. So f of t equals e to the minus 2t plus 2t e to the minus 2t. 3 mistakes to avoid. First, if the fraction is improper, divide before partial fractions. Second, for a repeated pole, do not write only one term. Include the whole ladder, like a over s plus a and b over s plus a squared. Third, check signs carefully. S plus 3 means the pole is at -3, not +3. That sign decides whether the time response decays or grows. Summary. Inverse Laplace in circuits is table matching after algebra. Partial fractions turn one complicated rational expression into a sum of simple modes. Distinct real poles give weighted exponentials. Repeated poles add t times exponential terms. Next lesson, we zoom out and read poles, zeros, initial value, and final value directly from f of s.